All right, good afternoon, everyone. Thank you for coming to this special joint EOL RAL seminar. Very happy to introduce our speaker today, Dr. Jennifer DeHart from Colorado State University. That's where she's a research scientist, but many of you know her as well from here. So just going back through her past, she has her PhD from the University of Washington, where she did her PhD with Bob Howes on terrain impacts on precipitation and hurricanes. And prior to that, in 2014, got her master's at Washington with Bob Howes as well on shear impacts and hurricane dynamics, and has led to some really important work that we use in the community today. And prior to that, all the way back to University of Michigan in 2010, where she got her bachelor's in Earth System Science and Engineering. Michigan is her home state. So her recent work has focused on heavy rainfall in MIU fronts and also in hurricanes and real-time observational analysis of hurricane wind fields, which I think some of the topics she'll be presenting on today. And her work stretches across many realms of studying basic dynamics, numerical models, and conducting detailed observational analyses. And part of that work stems in her extensive experience with field campaigns. I was looking back at your bio, and you were involved with field campaigns as an undergrad quite a bit, including Vortex 2. And then from there, went on to work with the Olympics and NASA HS3 programs. And then more recently, conducted pretty significant research with the Precip project that was in Taiwan, and also snow climb in Steamboat Springs. So she continues to collaborate here at NCAR, almost an honorary member of NCAR. She works across all the different labs within EOL's Lidar radar open software environment, LROSE. She works with us and RAL in doing observational surface wind analyses of hurricanes, and also has done work with collaboration with M-Cubed on tropical convection and MIU fronts. So without further ado, I'll turn it over to you. The floor is yours.
Thank you for the nice introduction, and good to see everyone here. Thanks for having me. Yeah, so today I'm going to talk about kind of two seemingly disparate projects, and I was trying to think how to link them. And the way that we're linking them is really these kind of open source radar synthesis tools. And so we're going to use those to look at two projects. And so this is work that I do at CSU with Michael Bell, but we have lots of collaborators, including Alex DesRosiers, who's currently at CIRA, as well as folks here at RAL, Jonathan Vai, Eric, Chris, Jun Zhang at University of Miami, and then Sam Irvine was an RU student at CSU one summer. Tyler Barbaro is a student with Michael, and then Anjali was a former student with Michael as well. So lots of collaborators through this work, certainly not us alone. So starting with just kind of the importance of open source tools, as the former LROSE PI, this is kind of near and dear to a lot of the work that I do, but they're really important for scientific advancement, and that seems somewhat blasé. But for example, thinking about radar data come in many different raw formats. They contain lots of noise and artifacts that need to be removed. And then even once you have this clean data, you have to do a lot of processing to retrieve physically meaningful products. And so to support scientific progress more broadly, all these tools need to be accessible, need to be well documented, and have pathways for community contributions to either fix bugs or identify improvements or new features. And this is summarized really well in this Heisterman et al. Paper from 2015. And so there are several groups that participate in this open radar science group. And I've listed some of them below, including PyArt, LROSE, et cetera. And so LROSE is just one package of many that exist, and it's co-developed by EOL, specifically Mike Dixon and Brenda Javernick, among many others, as well as CSU. So in terms of some of the products that you can create with packages like LROSE, you can first analyze like the echo, so your reflectivity, your polarimetric variables, and it can provide you a lot of different information. So for example, it can tell you about microphysics in terms of the hydrometeor identification, which is based on Vivek's paper shown in the, I can use this. In this left image, this is just a PID applied to Hurricane Florence from 2018, showing all this rain here in the green, and then as the radar beam gets higher, you get into the mixed phase and ice regions. You can also do convective stratiform partitioning that's shown in this middle graphic here. This is from Mike and Ricky's paper on echo. showing this new three-dimensional convective stratiform partitioning algorithm. And then on the right is a figure from mine and Michael's most recent paper showing precipitation rate from the precip field campaign, and this is using S-pol data. So there's all these different things that you can retrieve from radar. In terms of wind, another big tool that Michael and I use is Samurai. This was developed by Michael as part of his PhD work many, many moons ago. Sorry, Michael, if you're listening. But anyway, it's a variational global solver that uses cubic B-splines, which are shown in this image here. And that's used to fit data. And so you can think of it as a kind of multi-Doppler analysis tool, but you can add in a lot of other different data types. And recent work by Ting-Yu as part of her PhD work was to use this immersed boundary method that allows for wind retrievals near complex terrain. So now there's a better way of retrieving wind near mountainous places like Taiwan. And so Samurai, as I mentioned, supports data from a lot of different instruments, including radars, in situ aircraft, dropsondes. And I think it's nicely illustrated by these figures here at the bottom. This is from John Martinez's work as part of his PhD. This is from Hurricane Patricia, and it just shows, this left panel shows all the different data that went into Samurai, including the radar in black, the dropsondes are in red, the flight level in blue, and that allowed for this analysis of the overturning secondary circulation of Hurricane Patricia. So yeah, another very powerful tool. So as I mentioned, we're going to use these tools for two objectives, and really I'm going to be focusing less on how the tools work themselves and more on like the actual science that we can derive from them. So the first is the project that we're collaborating with RAL and University of Miami on. It's estimating hurricane surface wind speeds in real time. And basically we're using Samurai to synthesize NOAA tail Doppler radar data and in situ flight level wind data to create three-dimensional analyses, and then we can push it through a machine learning algorithm to estimate the surface wind. So that'll be the first part of the talk. And then the second part is improving our understanding of heavy rainfall processes, specifically in the Mayu front. And so we'll use Samurai in this work as well to retrieve the 3D wind field. And then we'll also analyze S-pulse polarimetric data to estimate surface rain rate and for microphysics and partition echo into convective stratiform. Most of the talk will be on this second piece because that's where I've had the most scientific involvement, but since I'm here at RAL, definitely wanted to highlight this project that we're doing. So with that, we will start with part one, the real-time surface wind speed estimation using the CSU SWANN algorithm. And this was, again, led by Alex DesRosiers as part of his PhD, but all of these other folks contributed as well. And this is under a NOAA HOT grant. So gonna try to highlight or give a brief overview of this problem. So surface winds are needed by NHC forecasters for the forecasts, for advisories, but most of the observations are collected aloft. So when you have the planes flying through the hurricane, you have a lot of in situ data. You also have the tail Doppler radar for the NOAA aircraft that gets remote observations and the dropsondes, but you don't have any direct observations of the surface wind. So historically, what's been done is applying these wind ratios, which have been based on dropsonde data, to reduce flight level winds to surface values. However, these, which is kind of illustrated in this profile here. So here's your flight level wind, and that's your actual surface wind. So calculating ratios to do that. However, the ratios that are currently in existence are a little bit simplistic, by necessity, of course, but things like the effects of asymmetric drag due to motion and eye wall slope are not considered. So very briefly, this is a plot from Kepler 2001. These contours show the wind ratio value, which I think I might actually define in the next slide. Sorry about that. But basically, you see on the top part of the figure, it's 0.7. At the bottom, it's 0.9. So there's an asymmetry due to motion. So Alex developed a neural network that predicts these wind ratios to hopefully incorporate some of this additional complexity into these wind ratios. This model is called the Surface Winds from Aircraft with a Neural Network, or SWANN. And it was trained on ratios, again, surface wind over flight level wind, trained on ratios of in situ flight level data from Jonathan Vai's Flight Plus dataset and the SFMAR surface wind. I don't have time to go into all the details of SFMAR, but basically it's a microwave radiometer that analyzes ocean emissivity to try and back out the wind speed. It's not a perfect instrument. I'm going to go into that in a little bit later, but it's kind of one of the best data sets that we have. So he trained the model on these ratios. And again, I don't have time to go into the full architecture of this model, but the model does show improvement over the kind of existing rules-based reduction factors that exist. And predictors that go into this model include the flight level wind, so what's observed by the plane or with Samurai, current storm motion and intensity. There's the normalized radius. Basically, you take your radius and normalize it by the radius of maximum wind, as well as motion relative angle. So if your storm's moving westward, you provide it the angle with respect to that motion vector, as well as the altitude of the aircraft, RMW. And so in real time, we're running this pseudo real time. And by pseudo real time, I mean I'm sitting there and like forcing the algorithm to go ahead. And all the flights, 2024 was a fun year. All the flights happened while I was on like work travel. So I was running this from Rome. I was running this from Montana, never in Colorado, which was very annoying. Anyway, so SWANN has run pseudo real time, and it was run for 2024 and 2025 seasons. And Samurai, where again, this is the wind synthesis tool, it ingests QC tail Doppler radar data that's provided by NOAA HRD, and in situ flight level data, which referred to as HDOBs, to get this 3D wind field. From that, we take the 2D flight level data. So oftentimes this is at 3 kilometers for the NOAA aircraft, though it could be at 1.5 depending on the flight altitude. But this is an example of what that would look like, flight level wind. We then push this data through SWANN. The neural net does its magic. And then we get out this surface wind speed on the right. And then we can provide that along with additional information to forecasters. So I have just a couple examples to highlight from Hurricane Melissa this past year. This is data from the P3. And so this complicated figure on the right is basically the figure that we've been producing. The Samurai flight level wind is in the center, surface wind is on the left, the actual pattern of wind ratios is on the right. And then we can also just put the raw in situ flight level data through SWANN as well. So that's shown here in this bottom left. And then for ease, I'm not sure how easy it is to see, but we have this table on the right that highlights the SWANN intensity values. For example, the Samurai Vmax was 165 knots analyzed. And we can also provide wind radii data, which are also used by the forecasters. So this is kind of the overview of what we provide. And so the good thing about the model is, again, I mentioned that motion asymmetry. So here you can see this is the wind ratios again. So we see an asymmetric wind ratio pattern. So again, we're capturing closer to theory than you would with these static thresholds. And so in terms of validation for this flight leg was 1330 UTC to 1400 UTC. And so the NHC Best Track values from that time were around 155, 160 knots. So we're just slightly above that, again, which this could be the better value. Obviously, we need to do more statistical validation, but at the minimum, we are within the range of what NHC was analyzing at that time. I have another example from the day before, same basic plot here showing from this particular leg. This is about 12 hours before the last one. We were analyzing 147 knots for the Vmax. NHC had about 152. So again, we're within that range. Oh, I should have mentioned the actual satellite presentation of Melissa is shown here in this plot there. Oftentimes, depending on where the wind max is relative to the plane, you'll get big differences in terms of the raw in situ flight data. So here it's about 10 knots different. And that's often because the plane doesn't always sample the max winds directly. But we can apply SWANN to the Air Force data as well. So you don't have any TDR data. This is just the pure HDOBs files. And so we can certainly run that, and we get here, for example, the Vmax was 144 knots, 140 knots, and these are the corresponding satellite images at that time. We're definitely lower than NHC at this point, but it turns out for both of these flights, the Vmax was to the right, or in this northeast quadrant, so the plane just wasn't sampling. So that is something, this kind of situational awareness needs to be considered. Another issue or potential issue with these Air Force flights is the center is more uncertain. So if you don't have a 2D wind field, the plane has to hit the center. So we can find the best center based on what the plane was flying, but if it doesn't get the center right. So there's opportunity for more uncertainties, but we've heard from the forecasters that they actually would really like it applied to this data because you often don't have the extra information that you do with TDR. TDR you can get down to about 0.5, 1 kilometer, whereas with Air Force flights, you can't. So this is like much needed, but we need to do a bit more. Maybe we need external estimates of the center and whatnot. But on the whole, we're quite pleased with our performance, but statistical validation is kind of the next step of making sure that we kind of know the error bounds and stuff. And so the exciting news was that SWANN made it into AWIPS this year. AWIPS is the kind of program used by a lot of the forecasters. Alan Brammer from CIRA sent me this very blurry screenshot of him putting the data successfully making it to AWIPS. So that was pretty exciting from our standpoint. And we have meetings scheduled with NHC coming up to continue to get their feedback on these processes. So just to quickly summarize SWANN, we've had quite a few successes. Surface wind estimates are promising and compare favorably to the operational intensities. We're capturing this motion, drag, asymmetry. Oh, I forgot to mention this. Maybe I'll go back quickly. Oh, it's kind of hard to tell. So one thing I did want to note, so yeah, SFMR has had some issues. Some are algorithmic, some are still being determined. So here in these Air Force plots, SFMR is plotted in black, and you see that the SFMR is greater than the flight level wind, which should not be the case. Friction would reduce the winds. And the good thing about SWANN is that even though it was trained on SFMR data, it's always weaker. So we're hoping that it's actually beating through the noise of some of these cases and not producing this false enhanced wind at the surface. So that's a success that we were really happy to see, especially given SMR issues. Yeah, so we think SWANN beats down the noise in many cases, but that's something we're continuing to work on, working with SMR scientists and other NOAA scientists to make sure that we have the best algorithm possible. Again, I mentioned uncertainty in the Air Force flights due to the center. And another challenge we currently have is that we have to wait for the NOAA TDR QC and synthesis to complete. That's when they send everything down from the plane. So we do have a pretty substantial lag because then we have to run our algorithm. But hopefully we'll be working to reduce some of that delay in the future. Our future plans include that statistical validation of SWANN with NHC Best Track intensities. We want to compare with other surface wind products, including instruments like SAR, that's a synthetic aperture radar. Though some of these, they're all kind of trained on the same data sets, so there might be some similar biases in all of them. And then we also want to integrate the CSU workflow with the RAL real-time TC-OBS system. So these are kind of the things that we'll be working on. So with that, I'm going to take a sip of water, and then we'll move into part 2. Okay, so jumping topics completely. Now we'll focus on work that Michael and I have been doing with several of his students, looking at the relationships between dynamics, microphysics, and rainfall intensity along the Mayu front during Precip 2022. So Precip was a really large field campaign across many institutions, as well as NCAR, funded by NSF. Supposed to take place in 2020. We all know what happened in 2020. Ended up getting delayed till 2022. Well, we collected a lot of really great data. So one of the science questions in Precip was, so the PIs really like to think about rainfall in this kind of intensity duration framework. So you can get heavy extreme rainfall through either really strong intensities or through really long events that persist for several days, or in some cases, events that are both intense and last a long time. But one of the key questions they were asking is, do these extreme rainfall events result from fundamentally different physical processes compared to ordinary rainfall, or are they just due to stronger forcing and an optimal combination of ingredients? So this was kind of one of the overarching guiding questions of Precip. As I mentioned, we're specifically looking at heavy rainfall within the Mayu front. So for those who are not, is anyone familiar with the Mayu front? I know some people are. Okay, so the Mayu front is a front that sets up in the Western Pacific in May and June of each year. It's shown in this satellite image on the left, this kind of banded feature. So the interesting thing about the Mayu front is it exists, or it's influenced by a wide range of scales. So the front manifests on the synoptic scale. It's kind of the boundary between this southwesterly moist flow and drier, slightly cooler, I mean, it's not really that cold, but cooler air to the north, it marks that boundary. It's part of the larger East Asian monsoon. And it's responsible for a lot of heavy rainfall. Apparently, Chris got stuck in a Mayu front like a decade ago, and it just rained for days. This case on the left is from precip. This is one of the dates we'll be looking at. This picture on the right is from 2017, which had a very strong Mayu frontal event causing lots of flooding. So this is a big, can really affect loss of life and property in Taiwan area. So it's called Mayu in China and Taiwan, I think Changma in Korea, and then Baiyu in Japan. So, and when we think of heavy rainfall, oftentimes we like to think of it in this simple ingredients-based framework. So this equation here is from a paper by Doswell et al. In 1996. I feel like it's a pretty classic framework. But basically, you can think of rain rate as a combination of microphysical efficiency, vertical motion, and moisture. Now, obviously, being in Taiwan, there's kind of ample moisture around at all times. It's a very moist place. That was one of the reasons why Taiwan and extreme southern Japan were chosen for precip. There's just lots of moisture all around, so you can kind of focus on the other ingredients. And because of the precip observations, we can actually address things related to the first two items. So in terms of the rain rate and microphysical efficiency, or even just like microphysical processes, characteristics, the polarimetric data from SPOL is really key towards this because it tells us about the shape and type of hydrometeors that are existing around this region. And because we have a sizable multi-Doppler analysis domain, there were a lot of, Taiwan has a really dense network of operational radars, and then with the addition of SPOL, NTU's TMAR radar, was it NTU or NCU? It was NCU. NCU's X-band radar, TMAR. You can do multi-Doppler analysis over like a sizable domain. So this really helps towards getting statistics. So in terms of today's talk, we're going to kind of break this up into two components. So the first part, or part 2.1, will focus more on the dynamics. And this is from a recent paper, or paper that was recently accepted to GRL. And then the second talk, we're going to focus on more of the microphysical structure. So the first part, we're going to quantify dynamics across rain rate regimes. Again, this is the paper that Michael and I just had accepted in, I think, literally 4 weeks ago into GRL. And so in terms of prior work, so there are somewhat limited statistical observations of dynamics related to heavy rainfall on the Mayu front. There's a lot of great case study work that I couldn't possibly fit in this talk. But there has been some prior profiler work in tropical mesoscale convective complexes, which is shown in this figure here. And basically, it shows that there's an increase in mid and upper level ascent when rain rates are higher. This is from Balsley et al. 1987. There's also work, I think, I'm not sure if I include it here, but Courtney Schumacher, as well as other people, have found similar results. Also, in terms of kind of quantifying dynamics, there was some work back in the 70s showing that Florida surface stations showed the size of convergent region correlates with maximum rainfall. But in terms of like larger statistics, there haven't been as much. There was some nice work by Chang et al. In 2015 that examined the precipitation efficiency of pre-funnel and southwest monsoon convection during TIMREX. And they found a similar upper level maximum of vertical motion, but they didn't really separate by rainfall intensity. They were looking kind of more at the overall structure. More recent work by Nielsen and Schumacher simulated a heavy rainfall event in central Texas, and they found that the most extreme rainfall regions were associated with meso-beta vortices, and then they found it was specifically the nonlinear dynamic vertical pressure perturbation force below the vorticity maximum, so really shallow, below 2 kilometers. That was really key to lifting otherwise less buoyant air to help increase the rainfall. However, this was in much more kind of supercellular dynamics. The buoyancy profile is different. But another of Russ Schumacher's students, Ali Mazurek, extended this work into tropical storm Imelda and using data from MRS, including low-level rotation track and gauge-corrected radar QPE, found that there was this is from Ali's work on the right, there was a correlation between rain and regions of stronger rotation. But again, they didn't really have the detailed dynamics due to the kind of spacing between the next-rad radars. And so thinking about rotation and rainfall, there's a few mechanisms where they could be related. So again, the nonlinear dynamic forcing from pressure perturbations, so that seems like it would probably be more appropriate in supercells. There's boundary layer convergence underneath rotating flow. You can have isentropic ascent ahead of PV anomalies and sheared flow. But then also, we know that rotation is a byproduct of other known rain-enhancing processes. So you have vorticity stretching in regions of ascent. So it could be a process or it could be a result of these processes. But thinking about all of this prior work, our scientific question was, do the dynamic variables scale with rain rate intensity? And so our hypothesis was that yes, that they would scale, and that I think also important is that they're not fundamentally different. You just see a systematic increase in those. So how we created our multi-Doppler analysis was we used 6 precip and Taiwan CWA radars that are shown in this figure on the right. Again, S-pole is kind of in the middle here. And it's a mix of different radar frequencies. S-pole is S-band. This is wrong. That should be S-band as well. We had TMAR, which is X-band, and we had some of the operational C-band radars as well. And the nice thing about all of these radars was they had fairly high Nyquist velocities, so we didn't have to do any de-aliasing. The one exception was this RCTP radar, which had a Nyquist velocity of 16 meters per second. So I had to face my fears of solo and go in and de-alias all of or I actually used a mix of PyArt's region-based de-aliasing and then had to go fix things with solo. And that was not fun. For anyone who's used solo, I apologize if you've had to suffer through it. But yeah, otherwise, thankfully, did not have to de-alias a lot of the data. We're looking at 2 different IOPs that were in the Mayu time period. The first one was IOP1, which was a 2-day period, and shown on the left here, this is the total rainfall from the operational QPE sums product. And this was a Mayu front with a back-building MCS. And then we were also going to look at IOP3, which was a nearly 6-day period with a quasi-stationary Mayu front. And so you can see with the second case, there was certainly a lot more rainfall with that, in part due to the longer duration, but also just more organized at times. So using all of this radar data, we created 545 analyses over these 2 periods, which are shown here with the corresponding contributions from each radar. All the analyses were anchored on S-pole's main PPI scan that occurred every 12 minutes. In order to produce the wind analyses, we used Samurai terrain. Again, that was with the additions that Tingyu did. We had a 1 kilometer horizontal grid spacing, but there is a low pass filter in Samurai that removes horizontal scales below about 4 kilometers. In terms of the polarimetric data, we gridded S-pole's polarimetric data to the same grid as Samurai. I was using a Radix grid. For the hydrometeor identification, we used the NCAR PID. Again, that's from Vivek's work. That's with, these applications are all LROSE applications. So Radix PID. And then the rain rate came from the hybrid NCAR QPE method, which is detailed by Mike's conference paper from 2015, using Radix rate. And we had to balance both distance from the surface with data coverage, and so we opted to select the 1.5 kilometer altitude in order to maximize data coverage, but certainly there could be additional changes below that altitude towards the surface. So here's just an example of some of the output that we have. Hopefully it's visible, showing the rain rate from 2 separate periods from this IOP. On the left, this is from S-pole, and then on the right is the Samurai analyses. And we're focusing on oceanic rainfall to reduce the impact of orographic processes and stronger diurnal processes. So that's why, especially in the rain, we've masked out everything that would occur over land. We're focusing really on this oceanic component. And what we see on the right here, again, is reflectivity analyzed by Samurai. The wind barbs are at 1.5 kilometers. And then the contours are rotation, where the white variables indicate stronger positive rotation. And so what we see from these 2 examples is stronger rotation is often co-located with the heavier rainfall, here shown in these purples. But it's not always. There's definitely some variation, and the rotation in this example is a lot weaker. But to statistically evaluate this, we did grid point by grid point comparisons over the ocean. Oh, again, I already mentioned the rain rate, 1.5 kilometers. And the kinematic variables we're going to look at include relative vorticity, vertical velocity, divergence, and then we'll also do some convective stratiform partitioning with echo at the end. So at each grid point, over all 545 analyses, we'll calculate statistics of dynamic variables. So the example is shown, where's my mouse? There we go. is shown here. So basically, we separate the grid points into 5 rain rate intensity bins, so 0 to 5 millimeters per hour, 5 to 10 milliliters per hour, et cetera, up to 50 to 100. And then we can plot the distributions. For example, this is vorticity for each of those rain rate categories. And here the distributions are all normalized. Obviously, there's a lot more data points in the low rain rate than there are in the high rain rate. But we do see systematic changes in the distribution. For example, here the weakest rain rate bin in the gray is much more narrow, centered around 0, whereas as you increase towards heavier rain rates, the distribution broadens to include both weaker but especially stronger positive rotation. And the mean value, if you kind of look at the peak of the distribution, shifts towards positive values as well. So we can do this, and I should note that this was done at 1.5 kilometers altitude. So we can also do this at multiple altitudes, which is shown here. On the left, I have that same 1.5 kilometer distribution plot, and on the right, I have the 5 kilometer and this is vorticity. And so we see at both levels, the vorticity distributions shift towards positive values and they broaden. So again, the practical impact of that is that you have more or stronger positive vorticity is more likely in heavily raining grid boxes than it is for lightly raining grid boxes. So again, they shift and they broaden. And thinking about the other dynamic variables, so here we have W on top, again at 1.5 kilometers on the left and 5 kilometers on the right. And then we have divergence, 2.5 kilometers on the left and 8 kilometers on the right. So this one is slightly further aloft to capture the signal. We see similar patterns here where the distributions also shift at higher rain rates. So for example, focusing on W first, we can see a much stronger and more dramatic. So there was a shift in the vorticity, but it's much weaker. Whereas the W, as we might expect, this is nothing new, that you have ascent in heavily raining grid boxes. But yeah, you see a strong shift towards this ascent. Your tail goes to even higher vertical velocities than you do in the lightly raining spots. And it appears to be more prevalent in mid-levels than it is at low levels. I do want to note, too, that, again, it's like a systematic shift. It isn't like some fundamentally different distribution that we're seeing, but we steadily shift from these lighter rain rates to these heavier rain rates. Similarly, as we might expect, we see consistent patterns with divergence. So that divergence is shown, excuse me, or these are negative values of divergence. So this is convergence, low-level convergence, and then upper-level divergence. And again, you see these very systematic shift towards, if you have stronger rain, you're going to have stronger low-level convergence and stronger upper-level divergence. And so again, this is what we expect, but it is nice to see it quantified and to see it kind of gradually change. These aren't fundamentally different. And be able to quantify this in a way that we haven't been able to quantify it before over a large domain. We can also just look at the mean vertical profiles just to confirm that this is true at more than the 2 levels I was showing. But basically, yeah, we see the same exact story. So here on the left is vertical profile vorticity going up to about 12 kilometers. And we see that the vorticity, again, as we go to those heavier rain rates, your mean vorticity value is a lot higher. And this extends up to about, 8 kilometers or so. There is this increase at upper levels, but as you'll notice here in the sample size, we're getting fewer and fewer samples, so this could be simply a sampling issue there instead, and less physical, because at those altitudes, you're most likely tapping into stronger convection. The low-level, the vorticity maximizes for the most part at low levels, which again might give credence more to the fact that this vorticity is more a byproduct of the fact that you have stronger ascent, stretching the vorticity, and potentially less of a forcing. But again, right now we just have kind of instantaneous correlations and patterns. You'd need more detailed modeling and budget analysis to actually get into the causal relationships. Here's the vertical profiles of W. Again, similar story. Increasing ascent as you get in heavier rain, and that ascent continues throughout this 12-kilometer profile that I'm showing here. And then if we look at the divergence profile again, very systematic shift towards stronger values in heavy rain. So deeper, stronger convection causes heavy rain. Again, not surprising, but it's good to have this quantified over this data set. We can compare the upper level dynamics with those from the Chang et al. Paper that I mentioned earlier. We notice similarities in the profiles. Again, these look functionally very similar. There is difference further aloft. However, they use different multi-Doppler techniques. We could be sampling different types of storms. It could be how we're averaging, how these different studies are averaging. So they're consistent, but there are some differences that potentially could be examined. And again, we were able to look at this quantified by rain rate, whereas this was more focused on the different storm morphologies. And then finally, last part of this section, we ran ECHO, Mike Dixon and Ricky's ECHO algorithm, which separates things into stratiform, mixed, and convective. So I've broken things down by rain rate again. That's this y-axis here with heavier rain rates on the right. And then within each of these bins, we have stratiform in this slanted line, mixed precipitation, which functionally just surrounds convective cells, in this dotted line, and then the solid bar is the convective precipitation. And unsurprisingly, as you move towards heavier rainfall, this is a log scale, you have orders of magnitude more convection than you do stratiform. And so the numbers here on top of these bars represent the fractional contribution to the total volumetric rainfall. So basically tells you how much of the total rainfall came from that particular bin. And you see the strongest numbers associated with these two bars. That's convective rain in the 10 to 25 and 25 to 50 millimeters per hour. This alone contributes almost 50% of the total volumetric rainfall. Stratiform contributes a lot less, though certainly these light rainfall rates, although they're very weak, 0 to 5, they're so frequent that they end up contributing a fair bit as well. But for the most part, it's these intermediate rain rates that contribute the most. And again, one could quibble whether these are truly intermediate rain rates. 25 millis per hour is an inch per hour, 50 is 2 inches. So it's certainly not, this is gonna be location dependent, but these 50 to 100 just simply aren't frequent enough to contribute more than about 5% of the rainfall. And so that's the end of this part. I'm gonna take another water break. So we're gonna finish up with looking at the dominant microphysical processes. So again, that's that part 2 of that ingredient space framework. And really what it comes down to is understanding the relative contributions of warm rain and ice phase microphysics. There was this study by Hamad et al. In 2015 that showed that deeper convection does not necessarily produce the heaviest rainfall, and the most prominent signature from the heavy rain rates is actually the low-level reflectivity enhancement associated with collision coalescence. But other studies have found mixed results on the importance of warm rain and ice phase. Every time you have a different radar, they have different paths of attenuation, et cetera. So yeah, Precip wanted to examine again how heavy rainfall differs microphysically from ordinary rainfall. And for a quick polarimetric radar background, so the great thing about polarimetric radar as opposed to single pole radar is that you get both kind of horizontal as well as vertical dimensions of the raindrops, hydrometeors, et cetera. And so 2 key variables that we focus on are ZDR, which is differential reflectivity, which is basically the ratio of the horizontal and the vertical dimensions of the raindrops. So in this cartoon here, basically as ZDR increases to positive values, your raindrops are more oblate. They more look like pancakes, so horizontal, which refers to big drops, which is how they grow. KDP, which is the specific differential phase, basically as KDP increases, your rainwater content increases. So you have both bigger but also more numerous drops. And so this is also, yeah, it's strongly related to the rainwater content. So in terms of actual microphysical processes, in the liquid phase, we can use these variables to get at different processes. So basically, in the liquid phase, if both your reflectivity, so Z, your ZDR, your oblateness, and then your KDP increase towards the surface, basically it means you have collision coalescence. You're getting more drops and they're kind of glomming together to create bigger drops. In the ice phase, it's a bit more complicated. So 2 processes, accretion and aggregation, have similar polarimetric signatures. There's a really nice series of articles by Matt Kumjian about just microphysical signatures in general. But basically both have increasing reflectivity and lower ZDR as you move towards the melting level. So if you only have microphysical quantities alone, or polarimetric quantities alone, it can be sometimes hard to distinguish between the two. The big difference is that accretion, you need supercooled liquid water to join onto the frozen drops. And then finally, we can use all of these variables along with lots of other polarimetric and kind of environmental variables like temperature to infer the rain and snow types. And so this is that particle identification that Vivek developed in the 90s. So we'll also look at that if time permits. So in terms of the scientific questions for this part, again, similarly, how does high intensity precipitation differ from microphysically from low intensity regions? And our hypotheses were that collision and coalescence and accretion are most important in high intensity, while vapor deposition and ice aggregation are important in low intensity precipitation. So we're going to do similar-ish statistics, except now we're going to focus on distributions instead of means. So similarly, we're going to look at each oceanic grid point over the 545 analyses, but now we're going to create CFADs. So CFAD is basically a fancy term for a two-dimensional histogram of whatever your meteorological variable is on the x-axis and then altitude on the y-axis. It's basically just a 2D histogram of, in this case, W, and how it varies with height. And then the black line here shows the mean. Similar to last section, we can separate CFADs based on rain rate intensity. So that's done here from, again, those same 0 to 5 up to 50 to 100 millimeter bins. So you can see how the CFADs change, shifting towards a more positive ascent as we move towards heavier rainfall. But sometimes it can be hard to tell the difference between these. So what we can do is normalize all of these distributions to make the maximum one. We can take the total sample CFAD and subtract it from each of these. So that gives you anomaly CFADs, which are shown here. And basically what they mean is red refers to more likely and blue is less likely. So for example, if we look at this high rain rate, it just really highlights the fact that these velocity values at these altitudes are more frequent compared to the mean, to the full sample, than these lower intensity and negative velocities. So it's just an easier way of pulling out the differences between each bin. So we're going to start with the liquid phase and collision coalescence. So we're going to look at reflectivity, which is on the top, and then ZDR, which again relates to the shape of the raindrops on the bottom. And here, again, weaker rain rate is on the left, strong rain rates are on the right, and then this line here denotes the melting level, so we'll focus below that black line for now. And so what we see is in heavier rain, we have more intense reflectivity values and more intense ZDR values. The values are stronger, they're larger. But in addition, we see in both the mean as well as the shape of this red, we see them increasing towards the surface, whereas they're much more constant at the weaker rain rates. So again, whereas weaker values change less towards the ground. So again, we have increasing values towards the surface, indicative of that collision coalescence process. We can also look at KDP. Again, that's related to the rainwater content, and that's shown here. Again, left is lower rain, right is heavier rain, and then here's the total CFAD just for reference. I should note that the way we calculate the rain rate is based on the polarimetric variables. So there is some, they're not independent at all, but we're going to look at the structure, not just the 1.5 kilometer. That's why you have this like strong artifact there. But with KDP, similar to DBZ and ZDR, we see both stronger values of KDP in heavier rain than we do lighter rain. And again, we see that increase. It's very noticeable in the mean towards the ground. Again, collision coalescence is occurring. So this heavier rain has larger drops. It has greater rainwater content. And then as I kind of foreshadowed in the background, in ice phase, signatures are less clear. So now we're going to focus above the black line here. We're going to look in the ice phase. And we see that if we look at, so the values themselves are certainly stronger in the reflectivity and ZDR, but the slopes are pretty similar between the heavy rain and light rain. So we have like increasing reflectivity towards the melting level, and ZDR is either constant or negative. But the nice thing about these precip analyses is we actually have W because we have both the polarimetric and the kinematic differences. So we can look at the different CFADs for W, and we see that, again, as we saw in the first section, we actually have ascent above the melting level and the heavy raining grid boxes. So we actually have the support to generate supercooled liquid water that you need for accretion. Whereas in the lightest rain, we do not have ascent. The mean is basically 0. So you wouldn't have the support to produce supercooled water, if at all, but if you do, it's minimal quantities in this lighter rain. So although we have similar signatures in the slopes here, we can actually say with pretty good certainty that, well, this is actually accretion because we would have the supercooled liquid water to produce that, whereas we do not in the lighter rain. This is just kind of confirms what we've already seen, but we can also just look at the CFADs of the NCAR PID for the different rain rates. Again, light rain on the left, right rain, heavy rain on the right. Here, dark green is heavy rain, and lighter rain is weaker rain. And these oranges are kind of grapple, wet snow, but again, more indicative of quantities that would have supercooled liquid water. Anyway, so basically this just confirms what we saw in the previous studies, but it is nice to see like, oh yes, we have this heavier rain here, and these signatures of supercooled liquid water aloft. I also want to note that this analysis is a reminder that the PID and HID methods are not perfect. We see all this orange, hail, grapple. Well, it's not all this. It's a small fraction, but there is some. So they're not perfect. It's always good to, critically examine the PID products that you're receiving. Anyway, so to conclude, we created 545 multi-Doppler samurai and gridded polarimetric analyses from 8 days of the 2022 Mayu period. In terms of our first hypothesis, that dynamic variables are more intense in heavily raining regions in the Mayu front, that's yes. We see that both in vorticity and W, and then also shift in the convergence patterns as well. They shift systematically to deeper, stronger convection. In terms of the microphysical section, were collision, coalescence, and accretion more important in high-density precipitation? The answer to that is yes as well. The combination of the polarimetric and the kinematic variables show that accretion and collision coalescence are critical in those heavily raining regions. And then finally, our future work that we want to dig into is determine the dominant processes behind these statistical relationships. That could be through budget analysis, modeling studies. We also want to dig more into the three-dimensional characteristics of individual updrafts, not just grid point, vertical profiles, and see how they relate with rainfall intensity in terms of where your W maximizes, things like that. Right now, we're also looking at smaller scales. The Mayu front is influenced by a wide range of spatial scales that need to be considered. And then finally, I think a lot of these results could be useful for validating numerical simulations and could help with, microphysical schemes as well as other things. So with that, I'll say thank you and take any questions.
All right, thank you for that very nice overview of all your work.
I know it was really long and I talked really fast.
No, it was a lot of great information. I hope that it will inspire some questions here in the room and online. So happy to hand it off to anyone here.
Very nice talk. I really liked all of your analyses. Very nice. I was curious about the vertical vorticity metric. You showed a map where you had reflectivity and then contours of vertical vorticity. And to me, it looks like often the vorticity is adjacent to the cells and not necessarily co-located. So I was wondering if your metric, I'm wondering if the stuff that's adjacent to the cell is actually not relevant and not captured in your metric.
Yeah,
or is that, and final, is that a Mayu front vorticity? Anyway, thanks.
So yes, this is just the pure vertical or relative vorticity from the samurai analysis. So that's a great question. That's definitely one limitation of our kind of vertical profile analysis. And it could be at, say, like a leading edge associated with the kind of convergent line and be slightly offset. And then, of course, precipitation doesn't just fall out directly. So that is something we haven't figured out the best way. I kind of alluded to this in the future work. One thing I want to do is kind of look at individual updrafts find a better way of like encompassing the full updraft structure and then be able to use that to look at the statistics and how that might change things. So it could be, I think the filters do help in that regard. The fact that the signal will be felt not just at that point. I mean, the statistics are still pretty good. There is definitely a relationship, but it could be contributing to the spread. Yeah, so that's absolutely. And then, yeah, it could be contributing to the spread in addition to all the other, whether it's actually a forcing versus a byproduct. So yeah, probably worth digging into. We haven't, yeah, I guess depending on like what the precip morphology was, we could look at things relative to the storms, like where things were setting up, but the storms looked quite different throughout the entire campaign. So yeah, it's definitely a really good point that we've thought about. Don't have the best way of dealing with it now.
And it might be just vorticity associated with the front itself too.
Yeah.
But I'm not familiar with that front, so.
Yeah, there is vorticity along the front for sure.
Yes, I enjoyed your talk very much, especially the polarimetric variables. And so here in Colorado, mid-latitudes, we think in terms of convection and rain rates. And then there was that famous CSU storm, Fort Collins storm. Maybe some people don't know, but we had that big flood back in 1996. And we found our rain rate estimators weren't very good, and we determined that, hey, it was a
The tropical.
warm,
Yeah.
how do you call the tropical rain? The warm
Yeah, it was the
rain
other
process.
ZR, yeah.
And so, how does that translate to the rain processes here? I mean, you talked about. I didn't hear that warm process rain rate mentioned very much. Is all these rain rates considered to be a warm rain process, or is there any kind of a dichotomy there that would fit into there, or it's embedded in there and I just didn't pick up on it?
Yeah, so the collision coalescence is very much a warm rain
rate process.
So, excuse me. Yeah, that gives you it gives you the DSD often associated with the more tropical-like air mass. So similar to specifically the 2013 flood. That was, I think, Katya's work showed that it was had tropical origin. So you get a lot more warm rain type processes, collision coalescence, where you're not dominated by big drops. So a lot of your average Colorado storm is going to be very big drop dominated. There's a lot more seeding from big hail and things like that. And you also, I think there's kind of environmental moisture component too. Like if you're in Taiwan, you have a lot more moisture. It's a lot easier to create drops. So yeah, it's definitely warm rain here. It's I think some of the precip colleagues, that's one of their goals is through future funding is because we did a preparatory campaign for precip. So we couldn't go 2020, 2021, NSF gave us a little bit of money to operate Chill, Chivo, and then SPOL, I think you were running SPOL at some point during that, and we ran. And so we want to compare the statistics across those two regimes where you have such different kind of microphysical processes. But yeah, this I would consider this warm rain. But you do what's also important. It's not only warm rain because you do have seeding from you have pretty strong reflectivities above the melting level. So there is an ice component for sure. It's just digging further into the relative contributions. And that can vary, even within this Mayu data set. You can have shallower updrafts, you could have deeper updrafts. So there could be variations between different cloud systems and stuff like that. But for the most part, yeah, the warm rain is really key to kind of tapping into that low level moisture and converting it from vapor into water. Yeah.
And would you expect, if you did the same type of an experiment somewhere in the mid-latitudes where you didn't have as much the warm rain process, would you expect similar results to what you're seeing here?
So it would depend on what air mass it's tapping into. So if it has a lot of Gulf support, you could see really strong warm rain. And it's not like you're not going to see warm rain at all. It would just be the degree to which and how strong it is and how much vapor you have available to convert. So I think you could, yeah, we definitely get warm rain processes here. I think the ratio is different. And we're starting especially at 850 millibars. The available moisture, the raw, grams per kilogram is a lot lower than you would see in Taiwan. So Yes, but probably less. But if you have like a strong moisture surge from the Gulf, like, yeah, again, with that 2013 flood, that was really strong warm rain. That's why the continental ZR relationship was so inefficient. Whereas if we'd had the polarimetric, the rain rates would have been better.
Okay, we have a question online from Aaron Dottery. Says, great work, Jen. Nice to see some precip analysis, and also has a question. I found similar results during my PhD, where storms with stronger vertical velocity increase the rainfall more in a future climate over the central U.S. I would be curious how you think the dynamic versus thermodynamic contribution could change for these Mayu storms with warming.
Ooh. Yeah, thanks, Aaron. Yeah, in terms of with warming, yeah, because obviously the Mayu thermodynamic environment is very different from mid-latitude. So the Mayu, you tend to be more in this moist neutral. So you get kind of what we call skinny cape. So your cape profile is skinny as opposed to mid-latitude where you get like a rocket shooting off, like if you look at the loaded gun soundings from Oklahoma. So it's a very different cape profile, and your W would differ. So there's definitely a difference between continental storms and the Mayu. So in terms of, I'm trying to think of the global warming impact on tropical. I know it's like a tropopause difference. I don't think you'd fundamentally change from like a not skinny cape, but you could change like the depth. You could shift the distribution over slightly. That's a really good question though. And then of course the downstream impacts on if your warm layer, like your above 0 degrees Celsius layer is deeper, how does that affect your partitioning into rain versus snow and ice? And how does that affect like fallout versus transport? It's actually really complicated when you think about the microphysics and like what. Yeah, but that's a really good question. I haven't thought about that, so I'll have to think about that.
Okay, one last quick question.
It may not be quick, because I actually have two separate questions. Can you go back to the first part of the talk where you're doing the wind work?
Mm-hmm.
And so what I was wondering is, that's fine.
Okay.
So you were computing those surface wind profiles from SWANN just as a line. And what I'm wondering is, could you give some uncertainty bounds to that line by varying the parameters and the predictors? And then if you have that uncertainty, then okay, it's going to be within the best track by the uncertainty and the algorithm in the parameters.
Yeah, that's a really good question. Because that's one aspect of why we want statistical validation, because that's one way of getting error bars. But that's also a really good point. I mean, we could do that with the 2D data as well. Mm-hmm. Most likely, you could create like a little mini ensemble. I guess you'd have to think about what exactly you want to vary. In my mind, I think actually one of the best things to vary would be the center location, since that can be uncertain, especially for when we have the 1D. The 2D, the center is a bit more stable. But yeah, I mean, there's a bunch of ways you could kind of conceive of an mini ensemble to get error bars. Yeah, I hadn't thought about that, but that's actually, because then you're not even really modifying the model. You're just modifying the kind of input script.
Yep.
So yeah, I'll have to chat with Michael about that.
Next question related to Aaron's comment is, when you think about like precipitation intensity, one of the parameters is the water vapor. So that actually relates very much to Aaron's question. So
if the water vapor increases, like Clausius-Clapeyron.
So I think
my brain.
So I think the real question is, do you go into some sort of super Clausius-Clapeyron relationship for these most extreme events? And that you actually might be able to glean from these data.
Yeah, that's a good question. And I want to stress I'm not a climate person. You probably could as like a first order, but again, as I was saying, you have to kind of take into account the full, like the buoyancy profile, how the microphysics would change, because all of these things affect like the pathway that raindrops would fall out and or, but certainly you're absolutely right that if you're,
Well, if it is superclausseous
Yeah.
clapeyron, then it is the dynamics. It has to be.
yeah. Yeah, it's a really good question. I don't have a good answer, but yeah, it's a, yeah. Yeah, I'm glad you asked that. It's a good one.
Okay, so, sorry we're a little past time, but I want to thank our speaker for coming all the way down from CSU to spend the day with us and present on our great work. So let's thank our speaker once again.
Thank you.